Okay, I think we should move on after the coffee breaks. So pleased to welcome Florian Knoll, who's from Erlangen, and he's going to be talking to us about limitations of deep learning for MR image reconstruction. Thank you.
Yeah, thank you very much for the introduction, and also thank you very much for the kind invitation. It's the first time for me to be here. It's really great so far. So this is going to be a talk for the deep learning reconstruction skeptics. So I'm going to show you several images where deep learning reconstruction goes horribly wrong. And hopefully also some guidance why things go wrong and what you can do or how you can spot when things go wrong or before things go wrong. So here are some of my disclosures, and also want to thank my collaborators and funding sources. When I did my PhD back in 2011, I was working on total variation-based methods, and we were working on image denoising, total variation. You can see that there are these staircasing artifacts, and then I was very, very proud that we were able to extend this model to second-order function, meaning now you have piecewise affine functions instead of piecewise constant functions, and we were able to get rid of these staircasing artifacts. So I was very proud of that we now have this image prior. And if you look at what we are doing right now, we have priors that have the computational capacity to synthesize MR images completely from scratch. So this is a generative model. And these are knee images that I have shown to musculoskeletal radiologists, and they were not able to tell the difference, that these are not real knees. So these models are incredibly powerful. But the danger is if you're doing it wrong, then you can end up with situations like this. So this is the same scan, the same patient, and obviously if you would diagnose this image, you would come to a very, very different conclusion based on reconstruction A and reconstruction B. So very powerful method, but also with great power comes great responsibility when we start to use these things clinically. So roadmap for the talk is I'm going to show you when deep learning reconstruction goes wrong, how it goes wrong when it goes wrong, and then a little bit about the underlying reason why this happens. This is going to be very, very fundamental MR physics. And it's probably the most interesting part at the end. Can you recognize when it goes wrong? So let's start with the first two. And just to set up the stage, I mean, we have seen this equation before. Not going to go into a lot of detail, but I'm going to talk about essentially methods where image reconstruction is formulated as an inverse problem, and then we have a data term here. So my image is U, my data is F, this is a forward operator, and we have some kind of prior information that is integrated in the form of this regularizer. And then you solve this optimization problem by means of some gradient descent sequence. So you take the gradient of this expression, perform a series of gradient descent steps, and converge to a solution. So and that leads to a formulation if you do iteration unrolling with a neural network, where you have a sequence of gradient descent steps. Each of them corresponds to one layer of the neural network, where you have a structure always like data consistency step and prior information, which is the neural network. So this is just the gradient of this expression, and the neural network is the gradient of the regularizer. So everything I'm going to show you today just follows this particular model. Yeah, and I'm just going to leave it at this with the theory. Just if you do this, I mean, people have demonstrated that this works very, very well, and methods are very, very powerful. So this is from a clinical study that we did at NYU a couple of years ago, where we introduced such a model in clinical knee exams, 170 patients, and on the top you see the standard clinical protocol. It's about a 12-minute protocol, and on the bottom is a slightly under 6-minute accelerated version with the deep learning reconstruction. And essentially, you can see that the images are identical, and all the pathologies that you see in the classic protocol, you also see in the deep learning accelerated reconstruction. And going beyond images, we really went through the effort of doing clinical readings for those, meaning our radiologists looked at all the regions that they would diagnose for this particular type of exam you would do in the knee. And we found essentially, I mean, the details of the statistics are in the paper, but we found that there's essentially no difference between using the conventional sequence and the accelerated sequence from the point of view of diagnostic information. Just another example, this is for cardiac imaging, where you can not only do qualitative interpretation, but also quantitative analysis. So this is a cardiac strain analysis, and what we compared was a deep learning reconstruction to the vendor compressed sensing implementation, and we could see in comparison to the ground truth that the vendor compressed sensing actually leads to a pretty significant underestimation of cardiac strain, which comes from temporal blurring, which works much better with the deep learning reconstruction. So far so good. This is when things work well, and this is another result. So this is not my result now. This is from the fast MRI study that we did together with Facebook a couple of years ago, where we handed out raw data to the research community and people sent back their results. And what I have here are the top 4 results from the competition. And I don't want to go into any comparison how much first place is better than fourth place. I would say they're all pretty much equal. I think the impressive result is if you compare to the image to the far right, this is a parallel imaging compressed sensing reconstruction that I obtained using my own method that I know inside out. I tuned it as best as I could. I cheated. I did an inverse crime. I looked at the ground truth and really tried to come as close as possible to the ground truth. And I mean, just the amount of difference, right, of this reconstruction to those of the participants that use deep learning reconstructions is just staggering, right? I mean, it doesn't even come close. This is a reasonable amount of acceleration, like 4 times acceleration. I also had a track there where we were really pushing things, like 8 times acceleration. So this is where you can actually see this effect amplified, right? So I mean, this is the classic reconstruction. These are all the deep learning reconstructions. So I mean, it's just stunning what you get. The problem is if you start to look closer. So here is a scenario where you have a pathology. So this is a meniscal tear here. And if you zoom in, then you can see that you see this tear in the ground truth, and it's lost in all of the deep learning reconstructions. And I think the key information here is this: it's not that the deep learning reconstruction lost this feature per se. If you look at the parallel imaging compressed sensing reconstruction, it's just a mess, right? This is just gone. And there's just no way, given these data that were measured, that you can actually reconstruct this feature. The tricky part is, if you give this image to a radiologist, nobody will read this. They would just say, yeah, image went wrong, scan needs to be redone, I'm not looking at this. These images, on the other hand, they look pretty good. And there is the danger that radiologists might have a false positive confidence and actually say, yeah, I score this, I don't see a pathology, because they're trusting images that, to a degree that the data actually does not support. And that's I think the biggest issue that we have with deep learning reconstructions. And so we tested this. Well, this is another scenario that can happen. Not only missing features, but also features that are artificially created. So for example, this is a feature from a blood vessel that doesn't exist, or this brain sulcus structure was inserted by the model, just does not exist in the ground truth. But these are very, very hard to find, I have to say. So in the challenge, we had several hundred images, each consisting of 20, 30 slices, and I hand-combed through them and found those 3. So it's very easy that features are lost. It can happen that they are synthesized, but it's much rarer. So we tested this, And we did a very, very simple experiment. Well, simple conceptually, really not simple in terms of compute. We took the entire fast MRI dataset, so close to 8,000 scans, multiple volumes, contrasts, and trained a gigantic deep learning model on the Facebook cluster. So all the compute in the world that you can imagine. And like hundreds of millions of parameters. And the experiment is very simple. So we just did a progressive acceleration from ground truth here, 2 times acceleration, all the way up to 100 times accelerated. So this is a 320 matrix. So what you see on the far right is an image that is reconstructed from 3 case baselines. So, I mean, essentially you see a blob, right? I mean, these are the zero filling reconstructions. So take a look what you get when you use the deep learning reconstruction for this, with this particular model. I mean, take a look at that. I mean, that looks like black magic. So, I mean, the fact that the model even gets out that this is a brain and it's the right contrast, it's T2 weighted, it's just stunning. The problem is, this is a very generic average brain. This is how you would expect a healthy average brain to look at, and there were thousands, tens of thousands of those in the training data set. Take a look what happens when you have an outlier case. So, I mean, here you have a pretty severe brain tumor, and you repeat the same experiment. So, again, zero filling, you just get something that degrades to the point where you just see a blob. This is what you get with the deep learning model. And this is worrying. Right? I mean, you see something that just still looks like a brain, but it gradually turns from a brain with a pathology to something that looks like a normal brain. So essentially, this is an average representation of what prior the model has learned based on the data it has seen. And I mean, of course, I mean, what do you expect, right? You gave the model no data. You gave it 3 case baselines. What is, I mean, you're getting what it has seen in the prior, right? And I think that's the core of the issue, right? I mean, you cannot simply expect to give the model no data and get a result that you can trust. If you think about it clinically, what they are operating somewhere here, right? And you could easily push it up to here and get a totally faithful reconstruction, but people don't want this. People want to go here, right? And then they are surprised when things go wrong. Right? So you just have to manage your expectations. This is another experiment where you can see this pretty well if you go to completely out of distribution. You take a model that was trained on brains and put a knee in there. If you go to the far end over there, like 3, 4 case baselines, you start to see brain-like structures. Like this looks a little bit like the ventricle here at the center of the brain. This looks like a brain cortical surface area that appears at the edge. So these are very simple experiments that you can do to see, okay, does my model actually break down? And again, this is, I know there are some non-MR people in the audience, so that's why I included this section. So why does this happen? What is the underlying reason? For the MR people, this is trivial, but if you just think about it, what you're doing in an MR reconstruction, parallel image reconstruction, essentially you're solving a system of equations. And so this is the most trivial case. Let's say you're doing an undersampling factor of 2, meaning you have aliasing, you fold 2 pixels on top of each other, and then you measure this with 4 coils. So meaning you get 4 measurements, and you have 2 unknowns. You're solving a system of equations. And in this case, it's an overdetermined system of equations. You can just do least squares. Life is good. If you change this to 5 times acceleration and 4 coils, well, what happens? You suddenly have an underdetermined system. So you have to use a prior to select the solution. There's just no way otherwise that you can solve this. And when you use a prior, you will see the effect of the prior. So this is an example, again, of a total variation reconstruction. So this is, in this case, 3 times accelerated. So 4 coils, everything is good. I mean, just, again, overdetermined system. If you go to 10 times oversampling, and you use a weak prior, then you end up with a blurry image, an image that's corrupted by aliasing artifacts. You have noise amplification in there. If you use a strong prior, and again, this is total variation, so you get an image that has a very blocky structure and appearance. You have to choose one of the two, right? And there's just no way out this. And the underlying reason why this actually works is simply because there's this inherent level of redundancy in images, and images are compressible. So, and what I find curious is that usually if you have critical systems, for example, space flight or airplanes, people like to add redundancy. Right? What are we doing when we do accelerated imaging? Right? We're taking the redundancy away. And then we start to see the effect of the prior. So the point I'm trying to make here is that it's not really the deep learning component that is creating these issues. It's simply that we are removing the redundancy of our process and we start to see the prior. It's just that the prior has a different appearance and introduces a different bias into the image when you do deep learning rather than a handcrafted prior. But it's not the inherent problem of the deep learning reconstruction. Okay, so what can you do? Right? How can you recognize how things are going wrong and maybe prevent this from happening? The classic way of doing it is to do Bayesian uncertainty estimation. So I'm sure there's going to be something about this here. So I actually don't want to talk too much about it. But this is an example where we trained a model where you're not just training one set of model parameters, but a distribution of parameters. And then you sample from this distribution, and then you can calculate a mean and a standard deviation. And essentially, that standard deviation shows you where is the model very consistent. It always gives you the same result. And there you say you have a low uncertainty, and where's a lot of variability. Right? And so these are the areas where there is a lot of uncertainty. And so this, I think, has been done for several years. It works really, really well. I want to show you a slightly different way of looking at this, and this is more coming from the MR physics. And the motivation is the following. What you're doing is you are looking at the pixel level variance of an image in the reconstruction with respect to all the pixels in the multi-channel complex input data that this image is reconstructed from. And this is an estimate of essentially the Jacobian. So, and the nice thing about this is that if you are doing a deep learning-based reconstruction or anything that is you do within your network, you get this information essentially for free, because in the backward pass, where you're essentially calculating these gradients, you have this information in there. You just have to take it out. This is not something that we invented. That was originally coming from Thomas Ernst's group at the University of Maryland in Baltimore. It was presented at the ISMRM here in London. But we now used it to study this pixel level variance of such a deep learning reconstruction. This is the example that I'm going to use. So this is now, it's a slightly simpler model. It's a single instance, like a zero-shot reconstruction, just to keep things a little bit simpler. But this is a deep learning reconstruction with variable strength of nonlinearity. So strong prior, very nonlinear prior over here. And here, everything is linear. So this is a linear network, which essentially corresponds to a classic Grappa reconstruction. So you can see that those two are identical. You get a lot of noise amplification. And over here, you don't get the noise amplification because the model regularizer is very strong, but at the cost of some blurring. So what do you get when you do this analysis? So essentially, this is equidistant Cartesian undersampling. So you're getting classic aliasing, multiple pixels being folded on top of each other. So this is 5 times acceleration. So you are getting 5 replicas, and every pixel in the image is being folded on top of each other 5 times. And when you do this variance analysis, then you can split up and see where the contributions of these corruptions are coming from. In the complete linear case, you are getting a single peak. So that means the pixel itself is having all the influence on the aliasing and all the corruption that it creates. If you start to introduce a nonlinear, like a deep learning model, then you start to see that what you don't see is this peak actually decreases, but the signal spreads out. So suddenly, pixels other than the core pixel, or we call it eigenpixel, also have an influence now on the variance of certain pixels. And the stronger you make the nonlinearity, the more you are increasing this background noise level, like the influence of all pixels, all of the image. And these are the components that you see from the aliased pixels. And if you then use this to analyze the reconstruction, so here you see at the top, these are reconstructions on the far right. This is a linear Grappa reconstruction. This is the deep learning reconstruction, but using a linear model. So this is identical to the Grappa reconstruction. And here you just have an increased amount of nonlinearity. This is the difference to the ground truth. So you can see, as expected, with the linear reconstruction, lots of noise amplification. Over here, noise amplification is really damped down, but you start to see some structure. Right? So this is when you have a ground truth available. But in practice, usually you don't have a ground truth. The classic way to look at this in the MR parallel imaging world is to look at G-factors. So this is essentially categorizing, gives you a pixel level map of how ill-posed the inverse problem is. So in the linear case here, you get a lot of noise amplification. And as you increase the strength of the neural network, the G-factor amplification is reduced a lot. So if you just look at this map, and this is classically what people are doing, things look good, right? You have less noise amplification, you're stabilizing the inversion, ill-posed problem is dealt with in a better way, looks all good. But then when you do this, consider this additional effect that you have, this blurring effect from the other pixels, you can create maps like these. We call those apparent blurring maps, and this is essentially the separation of the ratio of eigenpixel versus all other pixels. And you can see that as the G factor is decreased, the apparent blurring maps in the same regions are starting to get much higher values. So, and this essentially shows you, just from a pure MR physics point of view, it doesn't really matter which neural network you throw at it, where are the areas here where there is a lot of potential overblurring, hallucinations, are essentially a very, very strong effect of the prior happening. Okay, so this already brings me to the end. I hope I could show you a little bit of when deep learning goes wrong, how it does go wrong. It can lead to hallucinations, it can lead to overblurring. Talk a little bit about the fundamental reason behind it, which is essentially, well, you are solving an ill-posed problem, potentially even an underdetermined problem, and you are seeing the effect of the prior, and a little bit of a take-home message, like what you can do to recognize when things go wrong with this pixel level analysis.